Thank you very much, Per. Thank you all for this opportunity too. I really appreciate this. Real quick on who I am. I have a tendency to kind of approach this whole thing as an academic, so I really apologize in advance to everybody here. I do believe in learning by doing. So I'm an active member of the team, John Ripper password cracking team, and I compete in all the competitions that we have. I also really enjoy more standard, pen testing, red teaming types of exercises as well. So I compete in a lot of different capture the flag events as well. Probably the top one that I did though was my team made it into the DEF CON capture the flag finals, which was a real surreal experience. Because I don't know if you've been to Vegas there, but basically they put you all in the middle of a room, kind of like a zoo or something like that there, and then all the people come around, point at you as you're trying to Google, command line arguments and stuff like that. My day job, this is actually a hobby of mine. So I don't really do any password cracking at all. And so once again, I had to put a little disclaimer there saying that, this is not my employer. This is me that's saying everything here. In my day job though, I'm focusing more on medical device security, and that's just a really interesting field. And I really love it too because, a lot of times you have a job, it's like, okay, are we really making the world a better place? And it's really nice to be able to kind of do this type of work here and say, nope, no, we're actually really trying to protect people's lives here. Now, if you get outside of work and password cracking and stuff like that there too, I really do enjoy backpacking and hiking. And so about 4 years ago, I also took off 7 months from my job, and I ended up through hiking the Appalachian Trail. So I started in Georgia and I finished in Maine there. So if you ever want to talk about hiking there and embracing the suck, I will definitely be able to talk about that at length. So probably the really first question that people have though is when we say, what is PCFG password cracking? They ask, what does that PCFG stand for there? The technical, that was too a little fast there. So the technical answer is the probabilistic context-free grammar. So if you're really into, Serial Autonoma, or, you're a formal language nerd, like, maybe a few people back there, this might actually mean something to you. But for most people, they see that name there, and they're like, oh, God, it's math. I can't stand that. And it's like, whatever. So I like math. I think that's awesome. Basically, I kept on getting that reaction there. So I decided I went ahead to go ahead and rename this. So right now, it actually stands for pretty cool fuzzer guesser there, okay? And by the way, this is my favorite slide I've ever made in my life here, so it's all downhill from now. So, but this is probably a better explanation of, what we're actually doing here. We're trying to do kind of fuzzy guessing on how to create these password guesses. And another way of kind of putting this here is that we're using machine learning. And when I say machine learning, I mean machine learning in the traditional sense of like a whole bunch of if-then statements. So basically, we're not using neural networks or anything else along those lines. But what this allows us to do, though, is we can train on these disclosed password lists. So you have a list of all these different passwords. You use this tool in order to go ahead and parse these passwords. And then it basically generates a probability model for how it expects people to create passwords based upon this training set. And once you have this probability model, what this really allows you to do is crack passwords the same way that we talk about cracking passwords. Because we all talk about, oh yeah, people have a tendency to use their names of their pets, or family members, or they use birth dates as their numbers. They have a tendency to capitalize the first letter versus the last letter. And we use sports teams. And so you really want to go ahead and prioritize how you go ahead and incorporate that data in your cracking session. But you also want to go ahead and try kind of the less likely things as well, because cracking 1, 2, 3, 4, 5, 6 gets really boring really easy. That's the easy one to do. But you might want to go ahead and try like a really common word, like someone's football team, but then try a much less likely mangling rule on that as well. So trying to figure out how you go ahead and structure those different rules together is really kind of the core idea behind using PCFGs. So the original version of this here was actually developed back in 2008 when I was a graduate student at Florida State University. I had the really nice opportunity to be able to work in our E-Crimes Investigative Technologies Lab, ESIT lab. And basically, this was funded and done in the research here for the National Institute of Justice at America and the National White Collar Crime Center. So the real goal here was to be able to develop better tools for law enforcement to be able to crack passwords. And there's still a lot of that focus there, I would say, as well, with this. Now that was, over 11 years ago. So this tool's been out in the wild for quite a while. And I've, published papers because, I'm an academic. So other people have gone ahead and developed their own tools as well. So if you're interested in the actual, Florida's FSU ESET lab program there, that is pretty much only available for law enforcement. But if you're involved with that there, please go ahead and reach out to Sudhir Agarwal, and he will be able to help you out with that there. For this talk, though, what I'm going to do is I'm going to talk about these two different tool sets that I maintain currently right now and are available on GitHub. So whenever we talk about this here, this is really what I'm going to focus on. But there's a lot of other cool implementations out there, too. So part of the reason why I kind of want to give this talk, though, is because I just released a new version of this tool. And for this, I really have to blame Per. Because last year, he was asking me, like, hey, do you want to go ahead and present this PasswordsCon? And I was like, Sweden's a long way away, and I haven't really done a lot. Because, you have a research project that you've been working on for 11 years. There's times that you work on it a lot, and then there's a whole big period of time when you want to watch Netflix or something like that. So he was bugging me about this, and I was like, I really should go ahead and implement some new features. Maybe I can go ahead and release a new version before PasswordsCon. So my typical programming style here. I did not release a new tool before last year's PasswordsCon, and I ended up having a huge case of feature creep, where basically I started saying like, oh, this whole code sucks. I was tearing it out. I was like, I want to add this new algorithm, so I was putting in new stuff into it there, and I ended up completely rewriting the tool set from scratch, pretty much. So I finally was able to release it about 2 months ago, and so. Where the kind of focus on this here, though, was I really wanted to go ahead and move this tool out of academia and make it more useful for real-world use cases. There's a lot of new modeling features I wanted to add into this as well, and I'll talk about a few of them today. And then I also wanted to be able to go ahead and better support other cracking techniques as well. So in case you didn't want to go ahead and use the PCFG toolset itself, I have all this probability data that I'm using for parsing these password data sets. So it'd be really nice to be able to go ahead and incorporate this probability data in my more traditional word mangling rules that I would be doing for other cracking techniques. Another part of the reason why I kind of want to do this talk too, this is actually the GitHub page. I have a projects page on there that kind of details what I'm currently working on if you ever want to go to it. And pretty much the top one in my to-do list here is update PCFG documentation. I always fail at that. I hate writing documentation. So hopefully this will be able to provide a little bit of documentation right now for how to actually go about using this tool. Also, I want to point out that this is still under active development. There's a whole lot of things on my to-do list here, if you might notice. So what's really useful for me is if for comments back on people who might actually be using this tool about features they're really interested in. So that way I can move it closer up to the top of my to-do list, or maybe add new things to that as well. So PCFGs have been pretty popular in kind of the academic setting. So this is a Google Scholar. It's basically the Instagram for academics. It's just instead of likes, everyone kind of focuses on their citations instead. So the top tier results from doing searching for password cracking, at least when I did it, it'll change depending on who else does it here, is the original PCFG paper, which was cited by 366 people, and then a paper by CMU where they were comparing different password cracking algorithms, and one of them was the PCFG as well, which was also cited by even more people, 377. Everyone loves those cup labs. So what's really cool about this, though, is when I talk about how effective this is, or different aspects of trying to do this modeling here, I don't actually have to draw it into graphs, because I can just go ahead and go into everybody else's paper and grab their research instead. And that's really kind of be all nice when I be able to talk to you about why you might want to be interested in PCFG password cracking. Now, one thing I really kind of want to be upfront about, though, is if you look at all these academic papers, you'll notice something that kind of really stands out. And that is they really represent only very short cracking sessions. Because if you're not in password cracking and you say, oh wow, they made 1 trillion guesses, that sounds like a lot. But when you start looking at some of these different GPU-based attacks or something like that, you're doing that in like seconds. So PCFGs, there's a lot of computational overhead in that there, and that really does slow down your attack. So if you're trying to go ahead and crack like NTLM hashes or raw MD5, this is probably not the attack for you. You want to be able to throw something at it that can really keep your GPU happy. Where this is really nice, though, is when you're trying to attack computationally expensive hashes like file encryption. And in that case there, the cost of making a guess is so high that this becomes less of a bottleneck as far as how long you can run your cracking session. So I want to kind of go into this CMU paper here real quick here before I start diving into this tool set a little bit more, though. And the reason why I want to do this here is because there's always kind of a question, especially when you start talking about academic research, of how well does this represent reality? Do these grad students actually have the skills of a professional password cracker when they start doing this modeling here? And so this paper that CMU came out with here, they took a really kind of interesting approach. And so they compared different types of cracking styles. But one thing they did was that they got a security professional from CoreLogic to run a real password cracking attack as well, and to go ahead and model the results of that. And if you're not aware of CoreLogic, they're the people that run Crack Me If You Can at the DEF CON competition there. So I think it's fair to say that they're actually can be considered pretty good when it comes to password cracking. And we ran this attack when CMU modeled it here for pretty much the first trillion guesses. The PCFG was doing way better than the professional password cracker by trying to go ahead and create these guesses by hand. Now, when you start going ahead and giving them, this is a logarithmic scale, so they had 10 more times the guesses. They did eventually go ahead and beat it. But this is kind of really cool, though, in the fact that you don't have to have any skill. You just need to train it on a good data set. And you can have a cracking session that probably mimics or is roughly about as good as probably a real professional attacker here. So this is really good if you're going ahead and staying up a forensics shop and you may not have a professional password cracker on your staff, but they can do a pretty good job there when it comes to actually cracking passwords. Oh, yeah. So one other thing I just kind of want to point out here, first of all, though, is that academia is cool. And one cool thing about academia, though, is the ability to go ahead and influence change in the real world. So I don't know how many of you are familiar with NIST special publication 863B for digital authentication. If you read any of the older versions of it, you have the good old hits. They had this huge section talking about password entropy and saying that if you use these character creation rules and you forced users to have special characters and you made their passwords 14 characters, 15 characters long, it give you a certain number of entropy bits and it'd be equivalent to like a really long key. And it was kind of really pushing people to make longer and more complex passwords. So the updated version is much better. They got rid of that whole thing of password entropy there. And when talking about composition rules, they said in the official documentation, the most notable form of these is composition rules, which requires the user to choose passwords constructed using a mix of character types, such as at least one digit, uppercase letter, and symbol. However, analysis of breached password databases revealed that the benefit of such rules is not nearly as significant as initially thought. Also, the impact of usability and memorability is severe. And they referenced our paper because what we did was we ran PCFG attacks against a bunch of different password creation rules and showed that entropy really had no basis in reality. So kind of going back to Per's earlier talk though, also about password change policies. What are we doing about that? Everyone hates password change policies. Well, the FTC came out and it had a great paper by Lori Kramer that came out and said maybe we should really rethink password change policies. Maybe we shouldn't force users to change their password. And as part of that, she cited a paper, The Security of Modern Password Exploration, by some University of North Carolina researchers, where they went ahead against their university's own students there, because they had all the access to all that data, and they had about 10,000 defunct accounts they went ahead and tried to crack. And of those 10,000 accounts, they were able to crack about 7,700 of those accounts, at least one of those passwords. And then they started cracking it even more to figure out whether that password that they had just cracked there would allow them to go ahead and crack the new password. And they found, yes, it does. If you crack one password, you can pretty much crack all their other passwords pretty easily. And for that paper, these researchers used probably one of the earliest versions of the PCFG cracker there. And they said that the dictionary-based approach was most effective, especially when combined with the word list generating methods of the PCFG. So once again, this is one thing I just wanted to really kind of be really happy about, is that this is making your lives less complex when it comes to passwords here. So that way we can focus on things like password reuse and combating the real threats that users have to face. So all that's the kind of the background. Now I really kind of want to focus though on how do you actually go about using this tool set. And so I'm going to start out with the Python tool set that's available here. So the first thing you need to do is be able to go get it, and so you can get off GitHub. And as far as requirements in order to run it, really it's only Python 3. If you can run Python on a system, you can pretty much run this tool set here. I've tried it on a bunch of different variations of Linux. It runs on Windows. I even tried it on NetBSD, and it was about the only thing I've ever gotten to run on NetBSD. So I mean, there's not a whole lot of requirements in order to actually install and run this here at all. Now, one thing I want to really stress, though, is that this is only a password guess generator. This will not crack any passwords on its own. So if you really want to crack passwords, you also need to go ahead and have a password cracking tool of choice installed on that computer as well, like John the Ripper or Hashcat. And I'm going to use all John the Ripper examples because Hashcat's definitely had a good representation here, and I got to show some love to John. So the only other thing is just kind of an optional for training of data sets. There's this Python cardet module, and basically this helps you auto-detect what the character encoding the training set is, because character encoding is like the bane of my password cracking existence here. So that helps at least reduce a little bit of the stress of being able to do that. And I'll talk about that more when I talk about training. So one thing I want to really stress, though, because I was mentioning earlier, it's slow. The guesser is single-threaded CPU bound. So yes, obviously it's going to be slow just based upon that. I will make full use of that CPU, but you're not going to make use of any sort of GPU or parallelization or anything else really along those lines there. Also, it has very high RAM use. And the RAM use will continue to grow as it runs because the data structure is just keeping track of, just keep on going bigger and bigger and bigger. So I could have spent some time trying to do some more memory management. And I said, I'll just make people throw more RAM at the problem because that's cheap. So I mean, it'll start out not too bad, but for longer cracking sessions, I'd recommend at least 16 gigs dedicated directly to this tool here. So the next thing kind of is you need to start generating these guesses. The first choice you need to make, though, is what rule set do you want to use in order to generate these guesses based upon? Because this is, as I said, kind of machine learning. So you can have different rule sets depending on which target you're currently trying to target there. The default rule set included with the tool is trained on 1 million passwords from the RockU data set. So take that as you will. It's your typical online users there from back in circa 2008 or so. But you can definitely go ahead and have train on new data sets and select those as well. And I apologize in advance. I'll use rule set and grammar interchangeably depending on usually however I'm feeling right now. But basically they're the same thing. So once you have that, though, you just go ahead and start generating guesses. So the one script in order to generate guesses is PCFG_guesser.py. So that should be hopefully somewhat obvious. But you just run it as Python there. And it'll have two main flags. You don't have to add these here, but I usually recommend them. One is just the name of the rule set that you want to go ahead and generate guesses with. And then also I'd recommend including a session name as well. So because currently it allows you to stop or restart a session. So even if you don't think you're ever going to want to restart it again, it's sometimes nice to have a unique session ID because a couple days later you realize, oh, maybe I do want to go ahead and keep on that session going there. So I recommend having that and making that unique per sessions as well. So that's great to just generate guesses, but now you really want to crack passwords. In order to do that, you need to have a password cracking program. So with most of these different programs, Hashcat and John the Ripper, they allow you to go ahead and generate guesses and pipe it in versus in via standard in. So what you do with this is you go ahead and run the tool set. You give a pipe to it there, and then you use a flag like in John standard in. And John will start processing the input from this here, like you would have like a normal word list or something like that. Now, one problem with going ahead and running a cracking session when you're using something for piping in versus standard in is that these tools will often give you a great status report if you hit the enter button. But when you're running standard in, you hit that enter button, it doesn't go to John the Ripper or Hashcat. That enter goes to my tool. So if you really want to be able to go ahead and see the current status of your cracking session, at least with John the Ripper, what you can do is you can find the process ID of the John the Ripper process itself, and then to go ahead and send a sig user 1 signal to it by doing kill dash sig user 1 and then the PID of the Johnny Ripper process. And so from a different window. And then when it does that there, you'll get pop out here, and then you can see how many number of hashes that you cracked, as well as the current guessing speed it's guessing guesses at there. So in this case, it's about 4 million guesses a second. So it's slow, but it's not horribly slow, at least. Now I want to kind of take that window there though and go expand on that a little bit there. If I only had to give one slide for this entire talk, I would spend this entire talk right on this one slide here, because I think this really kind of shows the advantage of going ahead and using kind of a PCFG approach here. Because these are the passwords that it's currently cracking, and you can see kind of here, and I apologize for people in the back, but it's trying a whole bunch of different rules. And the great thing about these rules is I didn't have to write them manually by hand. Because if you're doing any password cracking, especially when you're generating these rules here, like, oh, I need to start combining these rules. So, okay, I want to capitalize the first letter and then add a special character and then some digits and so on. And that just gets very difficult here. So it's kind of fun when I look at these sections here to try to figure out, how did it generate this guess? What kind of micro rule did it use? So at the top here, I can see that it's trying, 5 letters and 4 digits in order to crack these passwords. But I want to specify that it's not trying all 5-digit words. It's not trying all 4-digit numbers. It's trying those words of a certain probability. So it might try, a 4-digit number, a word like love or something like that before it tries a word like chair. So you might see that cracked earlier in the cracking session before it gets to these things here. So if we keep on going down here, we see, Sess is cool, got cracked. You are cool, Sess, if you're watching. But in this one here, this was a multi-word. So instead of going ahead and trying something that's in your dictionary, it'll combine words as well. So, and I'll make this distinction a little bit here. Instead of breaking this up as like Sess is cool as 3 different words, what this is really doing underneath the hood here is it's trying Sess and then the combination is cool. Because that way it can quickly iterate between things. So it can then try Adam is cool, Bob is cool, and so on. Because that is cool is kind of a common occurrence. So it goes down here a little bit further, and it kind of looks like it's doing brute force. And when I actually dug into it, it wasn't doing brute force. It was actually just combining things like a Prince attack. So if you've ever seen Prince before, it's kind of a combinator. He throws a bunch of stuff at the wall and sees what works. And so that's really what's kind of switching off to right there. But then it tried 2 different kind of fairly neat rules where it's trying special characters of equal types around each one there. So once again, is this in your password cracking rule set normally? Well, it learned it automatically by training it on the data set here. And I could just, as I said, I could go through all this here, but even splitting down here, we have things like fingernail and 99. And those might be in your rule set, but in this case here, when I dug into it, these were multi-words again. So it's trying, finger plus nail and then 90 plus 9. And then, getting down here, then finally decided to go ahead and try, it's 69 settings, so it did 2 digits, in front of it with a capitalized word. And then finally, kind of at the bottom here, you're seeing even more combinations. So it's trying multi-words plus 2 digits. So like woodfish, 39, and taradon, 84. So you can kind of see how it starts going ahead and doing this. And now, also one thing I want to point out is this is about 12 minutes into the cracking session here. So all the really common passwords have already been done. So this is why we're starting to get into more kind of esoteric rules, because it's already tried, password 123 and 123456. So that's kind of what the PCFG is actually doing there. So when you do hit enter though, I did spend some time to try to go ahead and provide a useful stats output to you as well. So that way you don't have to kind of reverse engineer it. You can kind of really see what the PCFG guesser is doing at that time when you hit the enter key. So I hit the enter key twice, so these are 2 different stats outputs. But this first one here, you can see that it's actually doing multi-word guessing again. So it's trying the 143rd most common word in the front. It's doing no capitalization to it there. And then it's trying the 93rd most common word at the back. So it gets down to that level of fine detail there when it comes to generating these guesses. And in this case, the example would be like Kira and Ivan. Now, next time when I hit enter here, we can see that it swapped over though, and this is about a minute afterwards. So I hit enter about about 60 seconds afterwards, and it's now performing a brute force guess using the Omen ordered Markov enumerator. So it's swapped between those two different guesses, just in that, the guessing strategies just in that period of time. And if you keep on hitting enter, you'll keep on seeing it go around. So I did also, because I hate documentation, I tried to put documentation into the code as well. So if you hit H instead of enter, it'll bring up a status report help of what all these different things here in the status report means. And it actually, this help is way longer because it goes into the details of what these individual rule sets mean as well. But I figured I'd just cut that off for this presentation. But the one thing I really kind of wanted to highlight here is this kind of last option, which is probability coverage. And so when you hit enter, you'll see this probability coverage basically metric. And so one thing, and the reason why I add this here is that you always have to figure out when do you want to go ahead and abandon a current attack and try something new. So you've been running this for the last week. You haven't cracked the password you're trying to target. Should you move on to another case? Should you go ahead and just kill this and try some handcrafted mangling rules or whatever? And so this status report, this probability coverage here, tries to give you an idea about that. So what it does, it says it's an expected chance that a password would have been guessed at this point during the cracking session. And I want to stress, this is a fuzzy metric since it assumes that the target password exactly matches the probability of the training set. And the short answer is it doesn't. So this metric here will not be accurate fully. But at the very least, though, it gives you a good rule of thumb to say, okay, we've covered like 90% of the key space it expects here. This will basically run forever. It will never pretty much run out of guesses that way. But if you get like 90% or something like that, you might want to go ahead and just kill this off because every single guess it's making after this here is lower and lower and lower probability. So at that point there, I would probably recommend changing it. And then if you really want to go back to it, you have the save session so you can go ahead and restore it at a later point. So one kind of usage tip, because I want to kind of focus on actually using this tool too. And this is something that I just never really bothered with fixing here. But if this is generating guesses way faster than you are hashing those guesses, this status output will generally hang. It won't actually bring up because it doesn't bother to even check to see whether you hit the enter key because it's too busy trying to output guesses and getting blocked by your standard in. And so this happens quite a bit though if you're trying to crack like a bunch of bcrypt hashes because you're making 5 guesses a second or something like that. And so that will get blocked there because it's trying to make a million guesses a second. So that's kind of my to-do list, is to make that a little bit more easy to use there. So as I was talking about multi-word detection, this is probably the most effective feature that I've added in this 4.0 rewrite here. I added a lot of other things as well, but when I started seeing what passwords am I cracking now versus earlier, most of them were coming from the multi-word feature. So this was actually a really huge improvement for the accuracy of this here. So originally I was inspired by the work, the text multi-words by Sign in the Crack Staple tool set that he released there. Because one of the hard problems was trying to figure out from a training set, from a machine learning perspective, if something's a multi-word or not. It's hard to do because you can have like an input dictionary and compare it against it and try to break it up, but you get a lot of false positives. And also now you have to maintain its input dictionary. So now a new Pokemon character comes out or something like that, you want to be able to detect it in your training set, you got to go ahead and manage that. And that's a huge pain. And also this becomes very language specific as well. So now I have to maintain an input dictionary for Swedish. I need to have one for English. I need to have one for Mandarin, and so on. And I really didn't want to do that. So I spent a lot of time here trying to figure out. And currently, what this does is just identifies multi-words based upon solely on the training set itself. So if a word occurs by itself pretty frequently in the training set, it considers that a base word. It creates its own input dictionary on this. So this way, it can specifically target languages. And so this is really cool, and this does things, as I said, like kind of like pick up the newest band name or Pokemon or something like that without you having to go ahead and update it yourself. This is not perfect. This is kind of like it still will have false positives. It'll still have false negatives. So this will be something that's continuously evolving as well there. Also, probably the biggest challenge for this there is for a base word to be identified. It has to occur by itself in the training set. So that is also can be problematic sometimes. And I can talk to you afterwards about this too. There's a couple of different tweaks or something like that for common words like I love you, or like I love blank that are kind of hard coded in this as well, so that it's guaranteed to go ahead and pick those up. So I want to kind of go back in the Wayback Machine, though, for PasswordsCons, because this talk here by, I'm going to get his name wrong, and I apologize, Marcus Dumros, or at PasswordsCon 2012, this one slide caused me a lot of lost sleep. It really just vexed me. So I want to kind of highlight this a little bit here, but basically he came out with this thing called ordered Markov enumerator, which is a kind of a brute force type of attack. And if we zoom in at the very beginning of the slide, things look great to me, because I'm used to seeing all my tool at the very top, the most effective password cracker out there. So yeah, we zoom in at the very beginning, it looks great. Okay, I'm top, that's down there at the bottom. But if you let this kind of run out here, it just gets bloody. And I don't like that, and you'll notice that, when it's with the PCFG, it kind of hits this plateau. It doesn't do very much after that. And that's a problem because, and this is a kind of a known issue with it there, is that if you don't have something in a training set, it would never try when actually cracking a password. So if someone used a slightly different word that was never seen, it would never try that guess. If they used a number, for example, that was never in the training set, it would never try that as well. So it would do really good at the beginning, and then, after it's creating all these like lower and lower probability guesses there, it would just become basically not an effective attack after that point. So that's problematic. So I've been going ahead and making a lot of changes since 2012. This here is a more recent one from Sign's master thesis here. And this looks a lot better to me, okay? So this is pure PCFG versus Omen. Now this is a short cracking session though, but at least I'm on the top again there. But I want to be fully honest. If we run this cracking session for much, much longer, the same problem is going to occur. Okay, I'm still going to go ahead and exhaust pretty much all the passwords that I saw, combinations I saw in the training set there, and people are going to try stuff that just I didn't see at all. So eventually, if you run this longer, Omen will start to catch up and then surpass PCFGs. And once again, that's not acceptable to me. I really want to go ahead and have the best, most accurate password model out there. So I did what any typical academic would, and I went ahead and just kind of stole that idea. So I've incorporated with one of the Omen developers, Maximilian there, Omen directly into the PCFG grammar. And so what this means there is that it will go ahead and swap between your standard, more traditional PCFG attacks and these Omen, brute force type generated guesses there, depending on what the current probability was. Now, in order to do this, I had to go ahead and assign a probability to Omen guesses. So that's what pretty much all this here was basically me saying, okay, Omen works on probabilities. It works on these ideas called levels. So, it'll have, like a typical Markov attack. It looks at, what letter follows the next letter and it's kind of what happens there. So, if you see like JES, the next letter is probably another S for Jesus, of course, or Jessica, I mean. And the next one would be also U for Jesus, because those are kind of things that show up very common in passwords. And then if you get some things like JESM or JES2, they become much, much less probable. So the next thing I needed to do was calculate a key space for each of these different Omen levels. And then I go ahead and I try to see for these Omen levels here in the training set, how many of the passwords it would crack if you ran it against it for that Omen level. And once I have all this information here, I can go ahead and assign a probability to a level based upon each individual guess that it makes. So that way now I have a very fine-grained probability assigned to this there, and I know when I need to start going ahead and generating guesses with Omen versus trying to generate guess with another method there. And I want to be completely upfront, is one of the reasons why I love coming to these PasswordsCons here is I'm always looking at other techniques people are proposing as well, because I want to be able to borrow, integrate, and all that stuff in there as well. So I'm constantly, I'm very happy when I see more advanced techniques come out here in order to be able to kind of integrate it into this tool set. Now, but that being said, if you're actually looking at making use of this tool set here, one really effective feature is to be able to go ahead and disable that whole Omen integration. And there's a couple of reasons why you might want to do this. First of all, PCFG generation is slow, so you might want to be able to parallelize the work a little bit. So maybe you'll have Omen running in one session there, and then a normal standard PCFG attack another. So that will allow you to get a little bit more speed up and parallelize that work. The other thing, though, is that one thing I've been finding, though, is that, and I'll get into this a little more later, but finding good training sets is really hard. So a lot of times what will happen is you'll train on passwords where there's no duplicates in the training set. And you'll see this in a lot of dumps because they try to make it smaller. They don't include the username in the password. It's just a raw hash. The hash is not salted. So you'll only get things like password 123 that show up in your data set once. This is a problem, but for longer cracking sessions, it can be overcome a little bit with the PCFG. So it's still sometimes useful to be able to train on these data sets. But unfortunately, Omen itself really struggles when you train it on data sets that don't have duplicates. So in that case, I recommend turning off Omen guess generation and then running it, Omen on another data set that may not quite closely relate to the target you're trying to target, but at least it was trained on duplicates. So in order to do that, all you need to do though is there's a skip brute flag that you can have when you're running it, and then when you do that there, it'll skip all the brute force guesses. Well, I'm talking about turning off different options too. I might also mention you can turn off case smuggling for the PCFG guesser as well. So in order to do that, you just give it the flag all lower, and it will no longer do any case smuggling, and it will only generate lowercase guesses. So the question might be like, why do you want to do that? One option might be that the password hash is case insensitive. I don't really find that's really the case when you're using PCFG attacks though, because if the password hash is case insensitive, it's probably super fast to run and you're running some other attack against it instead. You're not going to be cracking landman with this tool here. Where I find it much more useful though is you might have an idea how your target is doing their case mangling, because people are very individualistic, or when they pick a case mangling strategy, they tend to follow that. So if potentially you've found out some of your other passwords, you might have an idea how that target is currently going ahead and mangling their case. So rather than trying all different case mangling strategies, what you might want to do is only try that specific case mangling strategy. You might want to try to capitalize everything, or you only capitalize the first letter, the last letter, or so on. And in that case, what you can do, and this is one thing that's really kind of cool that John Ripper supports, is instead of using kind of the stdin tag there, you can use what's a pipe tag instead when you're running in your John Ripper session. And what that allows you to do is then apply additional mangling rules to whatever you're pushing in on input. So that way I can have a traditional John Ripper rule set, and I can manually specify the case mangling rule I want to apply to this here. And then all the guesses I push into this here will have that case mangling rule applied to it there. So I've been talking about the Python toolset for a while. And so one really cool thing that kind of happened was I was talking with Adam, the creator of Hashcat, and he was interested in incorporating this into Hashcat directly as a slow guess mode, generating mode, which is awesome. I mean, I'm not going to say no to that. The problem, though, is that Hashcat is not written in Python. So in order to do this here, I had to go ahead and rewrite the entire guesser in C. And I hate writing in C. I don't know if I can write a hello world program with about 5 buffer overflows in a memory leak. So use this code with caution too. But so I went ahead and did this, and currently it's working actually pretty good. It doesn't have all the features of the Python toolset, and I always expect the Python toolset is going to be a little bit more feature rich than the C one, simply because I enjoy writing in Python there. So I'll generally probably go ahead and implement that there instead of this. So if you want to actually get this working, I really recommend contacting me first, because it is a little bit temperamental. Whenever you get compiled code running on random computers, that are not mine, it just behaves a little bit differently. But to try and make it a little bit easier, though, I am using kind of a modified version of Hashcat's makefile. So if you can build Hashcat on your computer, you at least have a fighting chance of being able to build this as well. But I've really only tested this so far in Ubuntu, or Ubuntu, running on Windows Subsystem for Linux, so that way I can run it on this laptop right here too. And then also, I'm never going to go ahead and have the machine learning portion that goes ahead and generates these rule sets written in C. There's just too many nice things in Python there for me to go ahead and make that transition. So you're always going to have to go ahead and use the trainer that's found in the Python toolset in order to generate new rule sets. Now, a couple other disadvantages, since I do eventually want to make use of Hashcat functionality versus having to develop myself. But in the compiled C version, there's no session save and restore. So once you kill it off, it's gone. You got to start over from scratch again. There's also no status outputs, because I want to be able to make use of Hashcat status outputs. And I haven't even gone ahead and implemented open guest generation in it yet either there. So those are some limitations. So the question was all those limitations and how hard it is to get to install and run, like why would you bother with this? And I personally have to say, I'm using this now mostly versus the Python toolset. And the reason for that is it's about 20 times faster than the Python toolset. And I always knew that Python was slow and C was fast. But when I saw that, I was like, holy crap. I was not expecting that big of a speed up there. If you need to be able to crack faster hashes, I would highly recommend going ahead and doing this instead. So I've been talking a little bit about guest generation, but now I want to kind of get into the other side of things here of how do we go about training these rule sets. So there's a lot of different reasons why you would want to go ahead and create a custom rule set for your target. So probably the number one thing is that language and country plays a large role in password creation. Now, at least for most non-Mandarin speakers, the actual mangling rules they do seem to be fairly the same to me. But at least the base words that they're choosing there are going to be very different. So being able to kind of customize that is really nice. And there's been some academic papers there that show that you do pretty good even if you train use like Rocky against a different data set like Japanese. You can do better if you train it really on Japanese passwords. Also, a big thing is that corporate password creation policies or password creation strategies tend to be a little bit different than what you see on websites. So if you're attacking corporate passwords, you probably want to go be able to train on corporate passwords first there, because people have a tendency that with password change rules and complexity rules and stuff like that there to do a little bit more than they do for their social networking. So the other kind of reasons why you might want to be able to do this is you're trying to target a specific password creation policy. So for example, if you train on Rocky, there's no real password creation policy in that at all. But you might be trying to target passwords that have to be at least 14 characters long, or have a special character in them, or must have an uppercase character as well. So you might want to only train on passwords that possess the characteristics that you're actually looking to be able to target. Now, you can also go ahead and manually edit these rules files by hand. I made sure not to include any sort of checksum or CRC value or anything else in these as well, because it's really nice to be able to kind of go in, open up the text editor, and just go ahead and say, I really want to go ahead and make this mangling rule specifically for whatever target I'm doing as well. And part of my to-do list is to be able to, instead of having to open up a text editor, is it provides some sort of like standardized GUI for people to be able to use as well for this here. But that's, I haven't done that yet. So the other kind of option here, and this is kind of highlighted in some of the talks here, is that this is really nice for being able to analyze current password dumps as well. So I might not be trying to go ahead and crack passwords with this here, but I might just be trying to figure out, what are the statistics around this password dump? How common are some of these words? What are some of the common mangling rules that they do? Where did this dump come from? And this is a really good usage for this as well. So you can run this on current password dumps that you're cracking or that you've obtained, and it can give you a lot of information into about what those dumps are. So I don't know how many of you are familiar with hashes.org. This is a great and wonderful site. There's a lot of different password hashes available on that there. But there's a lot of challenges when you want to go ahead and train on these data sets. So let's say you want to go ahead and, this has a bunch of different leaks on it there, so you can grab them. You have a general idea of where they came from, which is kind of nice as well. So like, let's say we try to do this like, I'm going to say it wrong, like, I'm not even trying to say it, but it's basically a Chinese website for graduates who are looking to be able to get new jobs. So that seems like a very interesting target demographic that you might want to go ahead and create a password cracking rule set in order to target there. So if you do this from hashes.org, the first thing is that you want to go ahead and train on only the plain text passwords. So don't go ahead and download like the hash pairs, because it's going to think that the hash is part of the password, and then it's just going to generate garbage. That's pretty much the first thing you really need to be able to do. The big problem with most of these data sets, though, is that they do not contain duplicates. And as I said earlier, duplicates are really important, especially for the very beginning of a password cracking session. Because if you don't have duplicates, it's not going to know that 1, 2, 3, 4, 5, 6 is a really common password. It's just going to look like a random number. It really helps to have duplicates in your data set. So if you can get a data set that actually does contain duplicates, you're going to do much better. That being said, as a password cracking session goes longer, that becomes less important because, and you probably already cracked 1, 2, 3, 4, 5, 6 using a different cracking session anyway. So being able to kind of get some of those base words and extract it out and really kind of target towards your audience is actually still can be useful in order to train on password lists that only contain unique passwords. Now another problem when you train on these data sets though is it only contains cracked passwords. You're not trained on the passwords that you haven't cracked, and those are the passwords you really often care about there. So it's a little bit like drinking your own bathwater when it comes to training on a current cracking session and then trying to rerun that cracking session against it there. So it really helps to be able to train on data sets that have a high completion rate of cracked passwords. Or plain text passwords are actually the best. So in order to use a trainer, it's also part of the Python tool set. It's called trainer.py. And basically you give it a name that you want to call the rule set there. And then you also give it the password training set that you want to be able to run it on as well. And it basically runs a bunch of different things here. And the first thing I really want to kind of talk about though is that encoding is really important. Now by default it'll try to auto-detect the encoding of the training set that you're learning on. But you can manually specify this as well if you are absolutely sure that you know the encoding that you want. And the reason why I'm bringing this up is by default, usually UTF is probably pretty good for a lot of different web passwords if you're trying to crack those. But when we start trying to crack things like file encryption, a lot of times the encoding for those will sometimes be whatever's set up on their local computer there. So you want to be able to target that specifically. In order to do that, you need to be able to train on a data training set that's of the same encoding type. So as I kind of mentioned a little bit earlier, password encoding is a pain in the butt. I try to automate a lot of it as possible. It's still going to be a problem, but at least hopefully this is helping a little bit out with being able to deal with some of these encoding issues there. So this runs 3 different passes through the train set, so it takes a little bit of time. The first pass through the train set, it learns the character frequency analysis and tries to figure out what the base words are for the multi-word guessing. And so this goes through pretty fast, especially if you're only dealing with like a couple million passwords. When you start trying to feed 1 billion passwords through this, it takes a lot longer. And it tries to basically keep everything in memory too, so it'll start using up even more memory as it goes ahead and starts passing through that there. So the one real main requirement when you do this though is you do need to be able to fit the entire password data set that you're training on in memory in your computer. So when you start dealing with these terabyte dumps of cracked passwords, you may not want to try to train on the full thing there. You might want to try only a subset of the passwords. The second pass through does much of the real parsing that we think about. So it goes ahead and assigns probabilities and numbers to case mangling to kind of masks within the keyboard walks and so on. And then the third pass through is really just for omen there. So it goes ahead and tries to assign probabilities to different omen levels based upon the information that it's learned. So after it does this though, it displays data about the data sets. And I'm still adding to this here of stuff that I find useful personally when I just want to be able to look at this data set and try to figure out where it came from. So for example, it'll post out the top 5 URL domains. Like the top ones will almost always be webmail accounts, so you can kind of ignore those. But what kind of falls underneath those there is often the site that the passwords were extracted from, because people always use site names and their passwords there. Also, it parses out dates too. Oh, sorry, I didn't. So it'll kind of list which years it's finding most common in the data set as well, because that's pretty easy to be able, or nice to be able to figure out, maybe when this data set got released. Now, there's a long tail. The current year is almost never the top most probably year, because people create their passwords beforehand and use that year. So you're really only seeing people who create passwords recently for the most current year. But you can kind of look at that to guess, like, okay, RockU, which is the data set here, 2008. That's when it got released. So one final thing I kind of really want to talk about though is PCFG attacks are slow, so it'd be really nice to be able to use this data in other cracking techniques. So who here knows about the Prince attack? And is it integrated directly into Hashcat, or you have to use a preprocessor for, or directly integrated in John Ripper? You have to use a preprocessor in Hashcat. It's a really nice cracking mode, and basically what it does is it just combines all the different words in an input dictionary together, and then hopefully you can crack some passwords with it. And it's really fast, and that's a huge advantage for that there. And it actually does a pretty decent job of cracking passwords. But the big problem with Prince attacks is generating those input dictionaries in the first place, because the success of your Prince attack is really going to depend on how good that input dictionary is. Because you need to both have words that you would expect to be able to build upon in order to do that. But you also need a lot of, for lack of a better term, junk in your data set or your set as well. So it'll do things like append 11 to the back of a password or append a special character. So if you create a Prince input dictionary that doesn't have all those values, it's never going to try them, and you're not going to crack a lot of passwords. The problem with a combinator attack, though, is that every single additional field that you add to that input dictionary there, exponentially increases the number of guesses you're going to have to make. So it's really a hard judge to be able to make up an input dictionary to be, contain all the junk that you want in order to be able to make an effective cracking attack, but not too much junk, so that way you never actually get around to cracking the passwords that you want. So since I have all this probability information, though, I can make kind of really nice bespoke dictionaries to be able to use in a Prince attack there. So I'll go ahead and it'll include a number of big words there, and a bunch of the smaller probability or smaller ones as well. And it'll only include the top X most probable values into this as well. So you can specify how big you want your Prince input dictionary to be. I've been finding that 100,000 words is probably kind of the sweet spot for being able to make a lot of guesses and having high accuracy. But you can really leverage that. So if you have a big GPU farm, you might want to have a really big input dictionary. So you can specify this here. So in order to be able to generate this here, basically there's another tool in the tool set called princeling.py. So you can run it, you can see the help thing, and you can go ahead and generate these dictionaries there. But the reason why I really wanted to focus on this first of all the different cracking attacks, though, is because Prince really is kind of like the lazy man's attack. Like, trying to crack passwords is actually, it takes a lot of effort if you really want to craft a customized attack there. You have to look at your target, you have to monitor your cracking sessions, see how you're doing, all this other stuff there. And sometimes you just want to be able to go out and have a drink and see, whatever. So Prince attacks, generally, that's the type of attack you want to be able to kind of just stroll onto your computer, keep those GPUs running, and then kind of walk off and still actually have a semi-effective attack there. So the problem with that, though, is I was talking about the input dictionary. It was a big pain in the butt to be able to always kind of worry about how to craft these input dictionaries here. So this just makes it a little bit easier. So that way, Prince attacks really you can just kind of like, okay, it's quitting time, launch a Prince, create a custom dictionary, launch a Prince attack, and run it. The other thing is really Prince attacks are actually pretty nice when you are going ahead and you have a crack list from the current set as well. So you look at, like, you may have only cracked 40% of the passwords. Let's go ahead, train it, create a custom input dictionary, and then launch a Prince attack with that there. And I'm hoping to be able to do this similar for other types of rules as well. But that's kind of an ongoing project for mine, to be able to create things like customized case mangling rules or customized normal dictionary rules as well. So that's pretty much it here. Does anyone have any questions? And